Okay. Good morning. I'm Barbara Landau, and it's my pleasure to introduce Tim McNamara, who's going to talk to us about Q integration in human spatial navigation. Tim's work has been for several decades, multiple decades, on human spatial navigation, spatial memory, and the nature of representation, and I've always really enjoyed reading his work. It's fantastic. I also learned that he has a dual role in his life. Not only is he professor of psychology, but he's also higher up in the administration at Vanderbilt. And he's been doing that as vice provost for faculty and international affairs, I guess, for almost 10 years. And so for that, I think he deserves a round of applause for just still standing. I give you Tim.
Okay, good morning, and thank you so much for being here to hear this presentation. I have a confession to make, and that is that this is the first time that these data have gone live, and the first time that I've ever presented them. So I'm still trying to figure out what our data mean, let alone the best way to present those data, so you just bear with me if I have some hitches along the way. So I'm going to be talking about Q integration in human spatial navigation, and how do I advance? Just click. I'm using Barbara's computer, her connector.
It's right there.
Yeah, great, got it. So this research is part of a long-term effort to understand the human spatial memory and navigation system. And our work has honed in on what we think are three major systems that humans use to navigate in the world. The one we probably spent the most time studying, probably 10 years, is what we call the environmental subsystem, which is basically just our long-term memory of spatial layouts, the environments that we walk and live in. We've done some work on maintaining orientation in the immediate environment, which relies heavily on path integration and so-called self-to-object spatial relations. And then we've done some work on place recognition and its role in locating us in the environment very quickly. Today I'm going to be talking about how these two systems relate to each other, and in particular I'm interested in how we combine information from different spatial cues to fix our position. So as you walked over here, although it's probably not a real conscious process, you had available to you many different kinds of cues to your position. Some were in the environment, landmarks, roads, and paths. Some of those were familiar, some were not. But you also had what are called body-based cues, idiothetic cues, about your own movement through that space, so proprioception, efference copy, vestibular cues. These two can be used to estimate position even though they are not uniquely informative about where you are. So we're interested in how these sources of information get combined. And the approach we used is inspired by Bayesian Q combination. I put Bayes in shutter quotes here because the approach we use really doesn't test Bayesian predictions in depth. To do that, you have to manipulate prior probabilities and posterior probabilities. We're assuming all those distributions are flat. And so what we're really looking at is statistically optimal Q combination, but nobody knows what that means in the literature, so I just use the same term everybody else uses, even though it's not really correct, and that's Bayesian Q combination. So the basic idea is that Q integration consists of a process of linearly combining information from different cues in the environment. They could be external environmental cues, they could be body-based cues. And the weights for those cues in this linear combination are determined by Q relative reliability. So what is Q reliability? It's just the inverse of response variability. So if we can imagine here that we have two Qs, B and A, and these are the distributions of those Qs, illustrating their variability. QA is actually more precise. The information is less variable than it than the QB, and in that sense it's a more reliable Q. Q relative reliability is just what it sounds like. It's the reliability of one Q relative to the other. And if the information about Qs is weighted in the linear combination based on their relative reliabilities, you get statistically optimal combination, which just means the variance of the combined distribution, illustrated here with this red figure, is minimal. So there actually is hardly any work at all in this area. There's a lot of work in Q sensitivity and Q competition, especially in the animal literature, so overshadowing and blocking paradigms have been used for multiple decades in studying animal learning. There's been some work on humans on Q competition, but looking at Bayesian, using a Bayesian framework to look at Q combination, as far as I know, there are really only 2 studies that have worked specifically with adults. One is the study by Nardini that Nora summarized yesterday, and another is an unpublished, as yet I think unpublished set of, it is published? No, it's not. Yeah, right. Unpublished. Yeah, unpublished work by Mintao Zhao, who is actually was a collaborator of mine at one point, and Bill Warren. And our paradigm, as you'll see, is actually very closely modeled after Nardini's, but is also inspired by Zhao and Warren's work. So what are we asking here? What we're looking at is how and how people integrate cues from the environment and from their body when those cues are varying in reliability. That's what 2 of the experiments deal with, and I'll talk about a 3rd experiment that actually looks at the effect of feedback on cue combination. So all of the work I'm talking about today is done in immersive virtual reality. So the participants wear what's called a head-mounted display. It's basically a computer screen in front of your eyes. So the only thing the subject sees is a rendered world on the computer screen. As they move, as they translate and they rotate, what they see is almost instantaneously updated, so it's a very natural experience in that one is feels like one is walking in this rendered animated world, which of course gives us great power as experimentalists because we can do things in virtual reality that are either very difficult or impossible to do in the real world. And Nardini and his colleagues did their studies in real reality. And did things like turn out the lights and have objects with fluorescence so that people could see them in the dark and so on. It was a very clever attempt to manipulate the cues. We can do this a lot easier in immersive virtual reality. So the task that we used is called triangle completion. It's commonly used in studies of self-orientation, path integration, navigation. It's really pretty simple. In our case, the subject experiences standing in this animated world that has an infinite ground plane with 3 landmarks here. I don't remember what they are. This is a water tower, I think that's a tree, and that's a church steeple. And while they're standing there, a red post appears, and the subject's job is to walk to the red post. And they're also told that they need to remember where that red post is, because at the end, they're going to have to walk back to it. They then walk to a green post that disappears as soon as they encounter it. They walk to a second green post, and then, why is that disappearing? It's okay. The environment doesn't disappear in general. That's just a glitch in the presentation. After they get to that last green post, they're told you need to walk back to that first red post. It's a challenging task, but people are pretty good at it because it's very natural. There's really no learning going on. It's something we do all the time. You get up in the middle of the night, you have to walk to the bathroom, you can't see too well. That's kind of what people are doing here. Now, it shouldn't be too surprising that in this task they make mistakes. And this is just an example of the scatter plot of possible locations that a subject might end up at after a series of trials. It's actually these data that we're interested in. We're interested in how variable that distribution is, and we're also interested in what the mean is, the centroid. And in fact, all of the analyses I'm going to present today are just based on the variance and the average response that they make over multiple trials of this task. So the experiments, I think they'll all, the first two experiments are all based on this design. I'll walk you through it. There are 4 major conditions, what we call a vision only, self-motion only, combination, and conflict condition. These all refer to the information that's available at retrieval when they have to walk to home base. During the initial encoding stage, when they experience the sequence of posts, they have all the information available. They've got the visual cues provided by the landmarks, and they also have body-based cues. Proprioception, that's feeling your limbs move. Vestibular cues, which are inertial. Optic flow, and so on. There is a brief interval of 20 seconds after they have learned the environment, walked the path. In one of those conditions, they're disoriented during that period. In the others, they just stand there and count, and that's just to make the conditions comparable in terms of the delay between encoding and retrieval. So in the vision-only condition, after, and I'll illustrate these later to make this more concrete, the subjects walk to the red post, the first green post, the second green post, and then they have to walk back to the red post in the retrieval stage. But when they do that, the only information available to them is the landmarks, because during this interval they have been disoriented, and so they lose all of their body-based cue information. In the self-motion condition, they walk the path to the last green post, and then they have to count backwards from numbers ranging from 2 to 300 by threes for 20 seconds. And then when they walk to the red post, they do so without being able to see the environment. They have to use their memory of their body-based cues to execute the response. In the combination condition, they're provided both landmarks and self-motion cues. There's no disorientation phase, and the landmark is visible again. In the conflict case, the landmarks and self-motion cues are placed in conflict by 15 degrees. And so the landmarks are telling them to go to one spot, their body-based cues are telling them to go to another spot, and somehow they have to resolve that conflict. So let's make this concrete. This is the vision condition. Subject starts at home base, sees the red post, walks to it, sees the first green post, walks to it, sees the second green post, walks to it. We then disorient the subject by spinning him or her in a chair so that they lose all of their self-motion information. And then the environment comes up and they have to use their memory of where the cue was, the location was with respect to the landmarks in order to figure out where to walk. In the self-motion condition, starts exactly the same in the encoding phase, but now they get to that last post and the environment completely disappears, but they are not disoriented. They just have to walk back to the red post. Remember where that first post was. In the combination condition, very similar, except in the retrieval phase, they're given both the landmarks and they still have their self-motion information. And in the conflict case, it's exactly like the combination case, except that the landmarks are rotated by 15 degrees. So the landmarks collectively are rotated 15 degrees so that they indicate one location, whereas the body-based information indicates another. So the idea here is in these so-called single cue conditions, the vision only and motion only, we have an estimate of how variable that information is that's available to the subject. And the idea is to try to predict their performance in the combination condition using their performance in the single Q conditions. And that's the basis of Bayesian Q combination studies. So the first experiment, we manipulated the reliability of visual cues, and we did that by using two environments. One environment was what we call a rich environment. It had 3 landmarks. So it has a lot of information, has more information about the location of a spot. You have distances and directions to each of the 3 landmarks, compared to this poor environment, which only has 1 landmark in it. So you do have distance, and there is directional information because this little flag does look differently depending on what direction you approach it, but is much less reliable, much less rich source of directional information than is provided in the rich environment. So I want to try to keep this talk at least at the 1,000-foot level and not get too deep in the weeds. We don't really need to go into these equations. But I do just want to run through a couple things. So this is Q integration. We have a combined estimate of location based on a linear combination of single Q estimates, where each of these single Q estimates is weighted by some weight. Q reliability, as I said earlier, is just the reciprocal of variance. Q relative reliability. So if we want to look at the reliability of QA, that's defined as the variance of B divided by the sum of the 2 single Q variances. So if the variance of A is fixed and the variance of B goes up, then the reliability of A goes up because A is more reliable than B is. This actually is a pretty crucial notion. It's response relative proximity. And the idea here is that in this paradigm, we're actually going to get 2 estimates of subjects' abilities to combine Qs in a Bayesian manner. One is based on looking at the variability of their response, yielding a measure of Q reliability. And those are what I will call the Bayesian predictions. But another measure is actually based on their performance in terms of their mean performance, the centroids of their distributions. So in this case, if we have a single Q distribution for B, so this is the performance when provided, say, only landmarks. This is the performance when, say, provided only self-motion cues. Each of these has a mean level. And this red curve is the performance when provided with both of those cues. We can look at the distance between the mean for A and the combined mean, and the mean for B and the combined mean, and construct an index of how much subjects were influenced by QA versus QB just based on those distances. And the idea is that the relative proximity to A, that is how close their mean performance is to the information provided by this Q alone, is just a ratio of the distance to B over the sum of the distances. So if, say, for example, A is fixed and B increases, that ratio is going to go up. What that means is that they're getting farther from B, staying closer to A, which means the relative proximity of A is actually higher. According to Bayesian theory, this value should equal that one. They should be identical. And to the extent they differ, you've got some deviation from Bayesian Q combination, which may or may not be interesting. It could be just due to random variation in response, but it could be systematic and important. Oh, one last thing. Bayesian alternation versus Bayesian integration. It's possible that people don't integrate the information at all, that they either use one Q or the other, and they select somehow. So in one trial, they might use just self-motion information. Another trial, they might use just the landmarks, even when both are available. If they alternate between those 2 Qs in a systematic manner, and in particular, if they alternate between those Qs with probabilities proportional to the Q reliability, then you get something called Bayesian alternation. That's the blue curve. Bayesian alternation actually gives you the same mean performance as Q combination, but it doesn't have the benefit of reducing the variance. And in that sense, it's not optimal. So it gets you on average to the right place. That is the right place based on the information provided by the single cues, but it does so with much less precision. And that's why this blue curve is fatter than the red curve. Okay, so what did we find in this first experiment? I'm pretty convinced this is not the best way to present these data, but I haven't yet figured out a better way, so you just have to bear with me here. So what I have here is response variability. So this is actually performance. Up is bad, right? So as they get worse, as the distributions get fatter, these bars are going to get higher. So lower means more precise responding. So one of the things you might want to look at, okay, did we manipulate anything here? Is there a difference between our rich condition and our poor condition? And the answer is yes. So the performance, that is the average variability in the rich condition using only the landmarks, is much better than the average performance in the vision condition, that is finding the red post using only the landmarks in the poor condition. This bar is a lot higher than that one. Whereas performance using self-motion alone doesn't differ at all. So that's just a manipulation check. It means we manipulated something. The second thing to look for here is whether there's any evidence of cue combination. Is there variance reduction when people have 2 cues versus 1 cue? And for the most part, there is. In the rich condition, the gray and the yellow bar are both somewhat lower than either of the single cue conditions. It's not a huge difference, but in this case it is significant. We've got something funky going on here where performance in the combination condition is actually worse than the conflict condition and statistically no different from self-motion alone. When we pool these together, and I'll talk later about the justification for that, it's really a methodological issue. We pool all these together, we get clear evidence of variance reduction, which is the key, sort of the signature of Bayesian cue integration, that responding with 2 cues produces more precise responses than using either cue alone. Is that, you follow me so far? Yes.
I just wonder, for the conflict situation, you manipulated it by the inverse sense, right? What would be the distance in the error you expect it should be?
The actual distance error? Boy, it's a good question. I don't know off the top of my head. Yeah. I don't remember how far the location is. It's not a big distance. In fact, there's some reason to believe that in a significant number of trials, the subjects don't even notice that there's a conflict. And that's one of the reasons I think it's justified. We can talk about that later. It's a very good question. I just don't know the answer. Okay, so this is sort of phase 1 of the data. Phase 2 is to say, okay, how does their performance compare to the models? And the answer is performance in the 2 double cue conditions, the combination and conflict condition, is pretty close to what's predicted by Bayesian integration and really far from what's predicted by Bayesian alternation. So there's clear evidence of variability reduction in the same ballpark as what you would expect from Bayesian cue combination. Again, we've got something weird going on here. In fact, what we think we have here is some kind of probability mixture or compromise between Bayesian integration and Bayesian alternation, producing this intermediate performance about halfway between the two. In the pooled data, in fact, this value here, this is performance in the combination condition, does not differ significantly from the Bayesian integration predictions, although there is a numerical difference. And if you do a Bayes factor analysis on this, it suggests that that null effect is real. Anything else I want to say about this? Okay, that's all the data. So these actually are perhaps the most interesting data that I will talk about in each of the experiments. Basically, these are the cue weights where we compare how they perform based on the distances between single Q and double Q conditions and the predictions you would get from a Bayesian model looking only at the variability of the responses. So these are predictions based on variability. These are predictions based on their actual mean performance. And if you look at this graph, and again, these are all relative proximities, vision relative to motion. So the higher the bar, it means the more they're weighting the visual cue. Over here, for the poor condition and the pooled, the predictions from the beige model, that's the light blue bar, are pretty close to how they perform. There's a significant deviation in the rich condition wherein people are actually weighting the visual cue less than they should. If you look at where they end up in the combined cue condition, they're not going as close to the visual cue as they should based on their performance in the single cue conditions. And this is where the action is, in my opinion. This is the correlation across subjects between relative reliability and relative proximity. For the rich, the poor, and the pooled condition, you don't need to be able to see the differences among those up there. It doesn't matter. The most important thing is this scatter plot. What it shows is that as subjects, subjects who perform really well on the visual cue, that's up here, also weight that cue much more than the self-motion cue. And subjects down here who perform relatively poorly on the visual cue also weight that cue relatively less. So it indicates that people are sensitive to the variability in their own responses and the quality of the cue when they combine them, even though their performance is not perfectly Bayesian, because if it were, all of these dots would be on a straight line. The other fascinating thing has to do with the individual differences in performance. People differ by almost an order of magnitude from down here to up there in terms of how much they weight visual cues versus self-motion cues. So this subject down here, let's look at this. Well, let's look at the red distribution. This subject, on average, by beige theory, should be putting 10% of the weight on the visual cue, whereas this subject's performance indicates that he or she should be putting in over 80% of the weight on the visual cue. That's a big range of individual differences, and to my knowledge, it's never been investigated before. No, this is actually pooled. They're conflict and combination condition pooled. Yes. In principle, it could. It doesn't in these data. It especially could if they stopped combining cues in the conflict condition, but the evidence in our data suggests that they're combining cues even then. It's not much. If we did this over again, we'd have a bigger spread. Okay, so what did we find? What we found was that the subjects were not consistently optimal in the individual environments, that the combination condition and the poor environment in particular seemed to be a compromise between cue integration and cue alternation. So there's evidence of some inconsistency with Bayesian predictions in the individual environments, that's the rich, poor environments. They are optimal at the pooled level, and Xiao Li conducted extensive simulations and analytical derivations to show that that optimality at the pooled level is probably not due just to an increased power, because you've got more data. And the data that I find at least as interesting as these is that these positive correlations between the actual weights that subjects apparently use when they're combining cues, where we're estimating those from their actual performance to what the Bayesian model would predict. Okay, experiment 1B is very similar, except now what we're doing, we're using only the poor environment, and in this, oh, I'm sorry, yeah. So experiment 1, we manipulated the reliability of the visual cues. In experiment 1B, we manipulate the reliability of self-motion cues, and we do that by introducing rotation of some amount before they actually have to execute the response. So in the no rotation condition, subjects walk to the various posts, they get to the last post, environment disappears, the head-mounted display goes blank, so they can't see anything, and their job is to walk back to the red post. So the only information they have available is the self-motion information that they have accumulated, remembered during the learning phase. The rotation 270-degree condition is virtually the same, except that after they get to the green post, we disrupt their self-motion information. We introduce variability by making them turn 270 degrees. They aren't disoriented, but there's this extra stuff that's added, presumably making that source of information less reliable to them. So these again are response variability. So this is actually a measure of how well they're doing. Up is bad. Looking first at manipulation check, we see that on average in the no rotation condition, subjects are doing better than they are in the rotation condition when they only have self-motion cues available. But there's no effect at all when they only have visual cues available, which would be predicted because the self-motion cues are absent. Especially at the pooled level, there's very clear evidence of cue combination. Variability in the combined and conflict condition is significantly less than variability when subjects only had one cue to guide them. There's some funkiness going on here where the combination condition is much worse than conflict. I don't have an explanation for that. Here we compare those same double cue condition bars now to the models, and at least at the pooled level, we see pretty consistent performance, that is performance pretty consistent with Bayesian integration, and in every case, performance really is not consistent with Bayesian alternation. And I'm just going to skip directly to this graph here because, again, I think it's the most interesting one. Here we again see these strong correlations, both in the no rotation condition, the rotation condition, and pooled, between the weights one would predict from their performance based on a Bayesian model. So these are predictions based on variability or precision, and the weights one gets from their performance, looking at their mean performance. Very strong positive correlations, huge individual differences on both dimensions, and yet nice strong correlations in the neighborhood of 60 to 70 to 80. Suggesting again that people are combining cues, if not optimally, nearly optimally, but there are huge individual differences in people's proclivities to use visual cues versus self-motion cues. And why those individual differences exist, we don't have a clue. So summarizing the two experiments together, I've got plenty of time. We see some inconsistency with predictions from Bayesian models in the individual environments, but at the pooled level, they're quite consistent with Bayesian predictions. And again, we see these strong positive correlations between actual weights and Bayesian weights. Okay, so last experiment I'm going to talk about. In this experiment, we wanted to see what would happen, how people would respond if they got distorted feedback on their performance. So usually performance evaluation and cue reliability, which is actually just a proxy for their actual performance, are really tightly coupled. You do well, you think you do well, I see I'm doing well. What we wanted to do was to introduce, we wanted to break that coupling apart. I'm not going to place too much emphasis on this top-down stuff. I don't really want to get into this at the moment. what I do want to talk about is this. What we did was to introduce distorted feedback with the goal of changing how subjects would evaluate their performance and, in turn, change how they weight the cues. So the idea would be we're going to tell people they're worse or better than they actually are, and our hope would be that when they combine that information with other information to determine where this location is in the environment, that they would weight the cue based on the performance evaluation that we provided. I'll make this concrete. We only used the poor environment. Subjects walk using their best estimate to where that first post is, and then they get feedback that says, you are 3 feet away. The feedback is provided verbally, but if they look around them in the environment, they see this circular array of posts, red posts. The red posts are actually 3 feet away from them. We put multiple posts here so they don't get any information about direction, so they don't know whether it's this post that's right, this post is right, or this post is right. What they do know is that they're 3 feet away from where they should be. And the diameter of this, the radius of this circle is 3 feet. So positive feedback, we inform people that they're actually closer than they actually were to the target location, where the target location is indicated by the blue diamond. And the verbal instructions in the head-mounted display might say, you are away by 1.5 feet. So they're actually being told that they're closer than they actually are, 2 feet. In the negative feedback condition, they were told, say, you're 3 feet away, even though they're only 2 feet away. And if we never showed them the actual target location, but if we did, it would be closer to them than the array of posts would suggest. Is that clear? So here's what we predicted would happen. So let's say this is a little scatter plot from somebody's performance using only visual cues. This is a little scatter plot based on their performance using only self-motion cues, and these are the weights. So we tell somebody that they're doing better than they are. That is, that their scatter plot actually has lower variability than it actually does. So this is what we tell them, even though this is what they're doing. Our prediction is that the actual weight would move closer to vision, even though the Bayesian weight would stay put, because the Bayesian weight is actually computed from the variability of their actual responding. Our hope was that by telling people you're better on the visual cue than you are, that the actual weight computed from their mean performance would move towards vision, that we could pull these things apart, see a separation between the actual weights and the Bayesian weights. On the other hand, if we tell them that they're worse than they are, that is, that they're more variable in responding, they're farther apart on average than they actually are, we would expect the opposite pattern of results. That is, they would weight the self-motion cue more. We had 2 groups. The vision positive group, people got positive feedback on visual cues and negative feedback on self-motion cues. The motion positive group, they got negative feedback on visual cues and positive feedback on self-motion cues. This is not the perfect design. I would much rather manipulate these factorially, but given the constraints of running subjects in immersive VR, which takes multiple sessions, very labor intensive, you have to push people around on chairs and stuff, we decided we would just go for the most informative conditions we could find, and these were what we thought they'd be. So is it pretty clear what we're up to here? Okay, so what did we find? I'll go through this pretty quickly. So first of all, do we have a manipulation here? It appears that we do. In the vision, well, actually, I'm jumping ahead. There's something really bizarre in these days. See if you can find out what it is. Completely antithetical to our predictions. Well, ponder for a while. Let's just look at cue combinations. So in the combined cue case, here people are doing better than they are in the single cue cases, and that's true in the motion positive condition as well. So these 2 double cue conditions are lower variability with 2 cues than 1. there's something weird. Yes.
The two gray bars are awfully similar, and the two yellow bars are awfully similar. Is that where you're going?
That's a good guess. It's not correct.
I think that's
What's weird is this. What's weird is that our feedback actually affected their performance. If we told them they were doing well with visual cues, they did better. And if we told them they were doing better, yes, it affected performance, not just the weight, it affected how they did. So in the vision positive group, on average, they're actually doing better than in the motion positive group when they're given only visual cues, and they're doing worse on the motion only condition. So this is vision positive, motion negative, right? And they're doing better here and worse there than they are in the motion positive vision negative. We did not expect this. People are actually adjusting their performance based on false feedback, not just their cognitive weighting of the cues. Well, this worried us because there's some possibility we got some kind of inadvertent subject selection, and you ended up one group with better visual cue users and another with better self cue users. 5 minutes, okay. Yeah, not close. So what we did was actually plot the relative weighting of the vision cues in the two groups separately across blocks of trials. And you see they start off identical. They start off weighting visual and motion cues the same, but as they start to get this feedback, you can see that they start weighting, the vision positive group starts weighting visual cues more and doing better on visual cues, and the motion positive group starts weighting motion cues more and hence visual cues less and performing better on motion cues. We still get the strong correlations between predictions from Bayesian theory and their performance. And let me just jump. So this is what actually happened in the experiment. What happened is we gave them the feedback, and they actually did better. That is, they were more precise. And then both of the weights shifted to the visual cue. There was a little bit of hysteresis in this, and I don't have time to go into it in detail, such that the actual weights lagged a little bit behind the predicted weights, and that's pretty consistent. We don't know why that hysteresis exists. And it occurred in the other direction as well. So, to wrap up, I've got like 4 minutes left. Yeah, I'm good. To wrap up, what we think we've shown here is that human navigators were able to combine cues in an optimal or near optimal manner. They did seem to be suboptimal at individual reliability levels. The most interesting data, to my mind, are the big individual differences we see in the extent to which people rely on visual versus self-motion cues, and the fact that those individual differences are reflected in their performance. So subjects who on average do well with visual cues weight visual cues a lot. Subjects who on average do well with just self-motion cues weight self-motion cues more than others. The curious finding from that last experiment where false feedback actually affected performance, not just the cognitive top-down weighting process. And then lastly, this somewhat, I won't even go into that. So just to wrap up, one of the big lessons to us anyway at this point from this work is the notion that cue quality is a multifaceted thing. This has not been explored much in the literature. Usually cues in the environment are talked about being good or bad. You know, they're salient or not. They're big, they're little, they're variable, they're not. That's it. But that's not sufficient. The way we usually think about cues is they've got some physical properties that determine response precision, and which of course is just our measured cue reliability. We can usually think of these physical properties as cue quality, so bigger, brighter, more stable, all yield higher quality cues. But what this leaves out is what we've shown, first of all, that there seem to be individual differences in the extent to which people can or will use certain kinds of cues. You can imagine those being incorporated into a pre-existing prior in a Bayesian model, although we've not played around with that all. We have situational changes, things that happen to cues while they're being used, and in our case, this is the experimental manipulations of the reliability of visual and self-motion cues. One can imagine that over time, that kind of variability, if you're experiencing highly variable visual cues for some reason, you might incorporate that information into a prior in a Bayesian model. But both of these are reflected in systematic individual differences. And so I think this, the multifaceted nature of cues and the individual differences in people's ability to use them, which harkens back to Nora's talk yesterday, I think is a really key issue in this domain of investigation. Thank you.
So I actually don't find what you thought was bizarre that bizarre. And the reason is because you have a lot of individual variability, as you kept showing and kept emphasizing, in how good people are or are not at using these various kinds of cues. Now, if you couple that with thinking about, well, why do you get that individual variability? Now, it could be like some people are just blind and they can't really use the visual cues, but it's more likely to me that it's attentional. And so if it's at all attentional, then it's very natural that they would adjust their attention to the relevant cue when told that they're good at it. And so from that point of view, I think you actually achieved what arguably, in retrospect, the manipulation was supposed to achieve. To do the alternation of the weighting, what I think would be more sensible is to take the conflict trials and to give them not just a circle around where they went, to give them, oh, well, you're actually off, it should have been there, and give them feedback that either more emphasized the visual cue or more emphasized the self-motion cue, thereby directly providing information on the weighting per se. Now, you could do that coupling what you mentioned as I think a very important next direction for this research, which is to not just use 15 degrees. I mean, you could use less, although they might not even notice that, but you could definitely use more, because there the prediction is once you get enough conflict, people pretty much know they have to choose, not integrate. And yeah, and that's also what Ken Cheng et al. Predicted in their Psych Bulletin review of this general literature, the one that he did with John Reiser, and yeah. But what we don't know is where the cut point is, which I actually think is very important because you should be able to predict the cut point from the variabilities. So those are, I think, important next steps. I think this is going to be really, really fruitful.
Yeah, those are all excellent observations, especially through by the first one, getting the feedback, getting people to pay attention to cues, and those people who are good at them will be even better.
I mean, you could maybe even look in your data for how. Exactly. Who alters? Like, do the good ones get better? Do the really bad ones, are they the one that improve, or what?
One thing that we don't know is the correlation between subjects' performance in the rich and poor conditions. So is it the case that
Right.
weight visual cues a lot in the rich conditions is also a dot in that graph high up in the poor conditions?
Mm-hmm.
Just true yesterday.
Yeah, that would be good to know. Right. I'll just pass it. You can then pass it along.
Just a quick clarification question. So when you actually did change the information that you gave them, and with the 15 degrees,
Yes.
they did perform better, right? So the bars were lower.
In some conditions, they actually were lower.
Yes.
It was rarely statistically
could that be related to something that there's sort of an innate sort of drift that you compensated for or something? So I'm thinking about like the inability to walk straight lines, for example, right? So
my guess is, and this follows, I haven't really thought this through all the way, because it just occurred to me based on Laura's comment. It's possible that the conflict is registered to some extent and causes subjects to pay attention. It's like, wait a minute, there's something weird going on here. I gotta really pay attention to where I go. And that could be why the average variability is a little bit lower in the conflict condition. I think really to get at that, we need to parametrically vary the amount of conflict or to manipulate attention directly. Does that answer your question?
yeah, I think the difficulty I have with that is that I would think that because the conflict is in the visual realm, not in the, I mean, because that's the one that you can manipulate, not in the motion information that they have. So I personally would find it more difficult to.
No, it's both. It's just that the two, we're manipulating where the visual cues are.
Yes.
But the conflict is between where the visual cue tells you to go and the motion cue tells you to go.
Yes. But yeah.
Well, there's no absolute frame of reference here. And so it's not, although from the experimental point of view, it's the visual cue that's wrong. From the subject's point of view, there's no reference. The subject doesn't know what's wrong. The subject doesn't know whether it's the motion information or the visual information. It just knows that they're different.
But yeah, but the subject so the input that the subject gets is visual, and based on that, the subject has to make the decision, maybe something's wrong.
So wouldn't the equivalent for a motion manipulation be something like weighting the subject, putting weights on the subject so that they actually think that they've moved a different amount from how they
We can do that.
I mean, wouldn't that be is that the kind of
Yeah,
Maybe this is your point. I know that from experimental reporting, we move the landmarks. We move the landmarks relative to the frame of reference that we know about.
yes.
But the subjects don't know about that frame of reference. But they're on a different ground plane. And so
No, but if they would be aware of that there's something odd,
yes.
that would be based on inspecting what they see, not what they feel, or the motion cues.
Well, no. Actually, it's the reverse.
Okay.
Let's talk about
Yeah, sorry.
I have just two short questions. So for those conflicting cues, the correct answer was reflecting the motion frame, ideothetic reference frame, right?
I'm sorry, I didn't hear your question.
For the conflicting situation,
Yes.
the correct answer was the one reflecting the ideothetic frame of navigation, not the allothetic one.
They're both correct.
I see.
If you only use the visual cues, you should go to one spot.
That's right, but
And
for
if you
your
only use the self-motion, you go to another. Now, it turns out that it's easy to think here that the self-motion indicated location is correct, but in fact, it's no more correct than the visual cue if you don't have a global frame of reference. If you use a global frame of reference, and if somehow our subjects were able to do that, then yes, the self-motion indicated location would be correct.
But for your measurements, how did you measure the error? Was it kind of reflecting the location that would my proprioceptive system?
We
lead
look,
me
yeah,
to?
we look at where they end up, and that forms a distribution. And then we looked at the distance between the average response in that distribution and the average responses in the single cue conditions. Maybe I'm not understanding your question.
We can speak about it later.
Okay.
But my second point is you mentioned the false feedback
Yeah.
influenced the responses, but not the cognitive mechanism. I don't understand this because I guess the response is the kind of consequence of cognitive processing. So Could you explain a little bit?
Yeah, so, I'm sorry I didn't make that clear. The idea would be that our hope was, we clearly failed, but our hope was that we could get people to impose top-down cognition onto this system and change how much weight they assign to the cues, even though those changes aren't justified by the actual reliability of the cues. And it's clear that we failed to do that. I'm not sure what else I can say along those lines. The Bayesian predictions are actually based on their performance, that is, how much variability there is in their responding. And our hope was that the variability in their responding would not change at all, because the only thing they're being told is that they're worse or better than they are, but that in combining the cues, they would use weights imposed in some kind of top-down cognitive manner that would yield different results from the Bayesian results. Now, maybe we're thinking about this wrong. And clearly we were thinking about the manipulation wrong because we got it backwards. Anyway, I think we need to...
I just think Barbara has the right idea. I think if you want to manipulate that, you should do it by messing up people's ability to do it, by weighting them down for self-motion,
Yes.
and giving them fuzzy glasses for vision.
Yeah.
I thought that was your idea. Yeah, right. Right.
I actually am also sharing a little bit of not understanding the relationship, I think, between doing better and changing the Bayesian model that you're using. So I guess, I mean, this I think reflects my lack of understanding of
Yeah.
sort of, the relationship between these two things. So you can do better, but still have the same sets of weights. Is that
Yes.
okay? So that's the discrepancy. You had hoped to
Yes.
change the weights, which wouldn't necessarily have any effect. How you perform overall is simply neither here nor there with respect to the sets of weights. You can perform poorly or well, and the weightings would remain the same. Is that correct?
Yes. I mean, essentially it all boils down to the fact that a mean and a variance are independent.
Yeah.
And the Bayesian model makes its predictions based on
the
variability
variance.
precision.
Yeah.
And the so-called
Yeah.
top-down
Yeah.
performance weights are based purely on the means.
So
So statistically it makes
Yeah.
sense. Whether it does cognitively, I'm not sure.
right.
And I think you're right. I think if we were to do this again, what we really should do, just to cover our bases and make sure we're not missing something, is to manipulate the discrepancy both in vision and in self-motion.
Yeah. Okay. I think we have to call the
Yes.
session. Thank you.
Thank you.